Good afternoon. Welcome to Krishna's classroom. At the outset, let me wish all the students who view this on this day a very happy New Year. I hope I will be able to record a number of useful lectures during this year. Okay, so with this brief note, let me begin. What I want to do today is to present the proof of the Urysohn's lemma. So let us first recall what Urysohn's lemma is and then systematically develop its proof. So we have the following scenario. X is a locally compact Hausdorff space. And K is contained in X. K is compact. For the V is contained in X. V is open and K is contained in. Now this is the basic scenario. These are the conditions of the Urysohn's lemma. Then there exists f belonging to CCX. That means a continuous function with compact support on X, which is non-negative and bounded by 1, such that f is identically equal to 1 on K and support of f is contained in. So this is the conclusion, and this is in very efficient language or notation is expressed as the meaning of which is given. So that's the theorem. Now, one of the crucial results that we use while proving this theorem is this, which we have already proved. With the same X and so on. Suppose U is an open set X and K is contained in U, K compact, then there exists V open. This result we will be using repeatedly, in fact. Then there exists V open X with compact closure . that is V closure is compact. Such that I can see that it's a closed set. V closure is closed. V is open. So K compact, open, P, P, and closure. Q is a given form. Or pictorially means the following. This is X. You are given a compact subset of that. Now what it says is, and there is an open set which cannot be bounded. No such assumption for that. Then what it says is that there exists a V. V is open. See, I am marking the boundary with the dots to indicate that it is open. And V closure is, I just draw this very close to V. So this is V. V closure is compact such that K is contained in V is contained in V closure. So the existence of such a V is stated in this result. And this is a theorem that we would see more than once. This proof. Okay. Now let us start working on the proof now. Okay. Proof of the theorem. See, the proof runs through 4 stages. The first is to a sequence of nested open V alpha such that K is contained in V alpha contained in V alpha sure contained in V. Oh, that's it. Okay, and there are several such things, and such that or let me just put this with some dots so that it is not mistaken for just one element. So we will put it this way. We use VR such that K is contained in. I will put few dots to indicate that it's a nested collection of sets VR that I am talking about. VR contained in VR closure. Then again, and eventually, so this is a collection of, so VR is a collection of open sets. So we have to first identify this. Okay. Now, how do we go about building this up? I mean, these are the integrity of the proof which are important for those who are learning now. How the whole set of nested open sets are built. So we begin with this. So step one, put R1 equal to and R2. Let be an enumeration of the rationals on 0. That means you are taking Q intersection the open interval 0, 1. And you know that this is a countable. Q intersection is countable and may be enumerated as R3, R4. This is the point. Now you see that, note that this enumeration is not in any conforming to the natural order relation. That means you cannot say that Rn is less than Rn plus 1 or any kind of the natural order is not assumed here. It is just one enumeration and we fix this enumeration throughout the proof. Okay, so there is a fixed enumeration. The proof, so we have this is possible because of the essential properties. Now, so what you have is this R1, R2, this is 0 and this is 1, the endpoints. Then you have R3, R4, etc. Okay. Now, this is of course contained in where R1 is equal to 0 and R2 equal to 1. That itself shows that all these Ri's are in between R1 and R2. So that itself shows that it is not any conforming to the natural ordering that you have. Okay. Now suppose, now this is the assumption. N is greater than 2. Greater than or equal to. That means we start with R1 and R2. This is the one. That is when n equal to 2, you get R1, R2. And we do this construction through induction. Okay. Then what you can do is the following. So you have K contained in, what is it? VR1 contained in P. VR1 closure contained in. This result is available by the previous theorem. Now we take R2. R1 corresponds to 0. Now we take R2. With R2, we have, now we take VR2 and where you place it, now this is the question. Okay, where you place it is over here. That means then there exists VR2 open such that, which you call V1 also, or rather, yeah, V1 such that K is contained in VR2 contained in VR2 closure is contained in VR1. Now you see that you have K, this is K, then you have, this is your V. Now first what we did was we identified VR1. This is This is VR1. Now its closure is compact. Okay, VR1 is compact. Now what you do? You take K and VR1. K is compact, VR1 is open. Therefore, you can identify VR2 in between. Okay, such that K is contained in VR2, is contained in VR2 closure, and VR2 closure is a part of VR. So this is what you get. So that's the beginning. Okay. Now suppose all this is based on the theorem that we have quoted, that there exists such open sets. Suppose greater than or equal to VR1, VR2 Rn have been chosen such that Ri less than Rj implies Vrj closure is contained in Ri less than Rj. This reverses it. So this shows where you have to, how, in what order they would be appearing. Okay. Suppose this is done. You have got V1, VR1, VR2, etc. VR. Okay. Now, how to construct, how to adjoin this collection, and where do you so this is the question that you encounter. How to pick this Rn plus 1, Vrn plus 1, and where do you place it? So here we have seen that VR2 has been placed between K and VR1. Okay, so remember this is the order, the way in which it has been constructed. That is Ri less than Rj implies Vrj closure is contained in Vri. So that's the basic idea. Okay. Now let us see how we do this. And this is probably the tricky part in this course. Okay. What one does is the following. So already you have this enumeration. R1, R2, this is fixed. This enumeration is fixed. So up to this we have handled. Now we take Rn plus 1. Choose or pick Rn. Now what we do is we split R1, R2 Rn. Take V R1, R2, Rn Now we identify or we denote by, let Ri be the greatest number among R1, R2, Rn, such that Ri is less than Rn plus 1. That means, you see, these are finitely many numbers and Rn plus 1 is 1. Now you see that Rn plus 1 is not among this. Now you split it up into two classes. All the numbers among this which are less than Rn plus 1 and all the numbers among them which are greater than Rn plus 1. Now this is possible. Okay, there is at least one number greater than Rn plus 1, namely R2. R2 is 1. Okay, R2 is 1. So that is the largest rational number that you have on the compact interval 0, 1. Okay, so Rn plus 1 is at least behind R2. I mean, it's certainly always behind R2. Okay, right? So you have numbers which are less than a finitely many numbers which are less than Rn plus 1 and finitely many numbers which are greater than Rn plus 1. So let us bring that also in. Let Rj be the smallest number among Rn greater than that means you are taking the natural order and in which you are placing this Rn plus 1 greater than Rn plus 1. This is how we do it. I mean, I'll just show you practically how this comes up. What is the consequence of this? Then Ri is less than Rn plus 1 less than Rj. And by our choice, how would this Vrn plus 1 should be placed? Okay, we have Vrj closure is contained in Ri. Okay, Vrj closure is contained in Vri. This is what you want because we have Ri less than. Okay. What it says is that, see, in between these two, there does not exist any V up to this moment because we have not constructed. So you get, you are back to the problem. See, this is a compact subset of X. This is an open subset of X, and there exists a open set which you would prefer to call Vrn plus 1, such that Vrj closure is contained in Vrn plus 1, is contained in Vrn plus 1 closure, is contained in Vrn. Okay. So, there are many, in fact. This is what we name it, such that Vrj closure is contained in Vrn plus 1, is contained in Rn plus 1 closure okay, VR. This is possible. So we have identified Vrn plus 1 quotient. I'll just give an example. The example is to understand this. Suppose we have enumerated R1, R2, etc. So 0, 1, 1 by 5, 7 by 8, 3 by 10. So this is the enumeration. 2 by 3 and 3 by 4. So that means you have got R1, R2, R3, R4, R5, R6. Suppose R8 is, cannot be any one of this, it is something different, 3 by 7. Then what do you have? To see that the set 0, 1 by 5, 3 by 10 is below 3 by 7, and the collection, what is it? The 2 by 3, 3 by 4, 7 by 8 are above 7. Okay. Therefore, you choose the greatest among this and the lowest and the smallest among this. So, what is that? Ri is equal to 3 by 10, Rj equal to 2 by. So, you have 3 by 10. This is the one which is between these two. This is your Ri and this is your Rj. Okay. Consequently, what will you have? Consequently, what you have is this. You have V 2 by 3 closure is contained in V 3 by 7. So this is the one that we are after. Okay, there exists such an open set, and this is contained in V closure is contained in V3 by 2. Sorry, this is I believe 3 by 10. Okay, 3 by 10. V. So essentially, you are placing V 3 by 7 in between V 2 by 3 closure and V 3 by 10. This is open, this is compact, therefore such an open set do exist. I mean, does exist. Okay, so what do you have? So this is just how to clarify how you actually do the picking of the slot where you should fit this Theorem. Okay, continuing now, we can continue. We obtain a collection open sets. We are one corresponding to each R belonging to Q intersection I can put here because already we have given. Okay, such that K is compact open, and such that for S greater than R, Vs closures containing, get the relation S greater than R. It is not Vs closure greater than Vr. This Vs closure is contained in, this is compact, this is open, Vs itself is open. So this is how the construction goes. So we have now obtained a sequence of what are called open sets packed between the K and V. Okay, it's a nested open sets. If you just try to work this out on R, taking X as R and then K as some compact subset, namely say some closed bounded interval, because closed boundedness is equivalent to compactness, and then try to pack it in then try to find out open intervals which are sort of nested intervals doing the same sort of thing. Now the step 2 is construction of Fn. So this is the sort of thing that we do. So for that, define f r x to be equal to r for x belonging to Dr and 0 otherwise. And Gs you define as equal to 1 for x belonging to S quotient and equal to S otherwise. Now let us spend a moment to understand this. Okay. So I will take up the real line analogy to be clear, if you can easily translate into a schematic diagram. Okay, so but it's more visible. Take the interval, take the real line. So you take some compact interval AB. Okay. Now suppose VR is some open interval CD. So K equal to the closed bounded interval AB. VR equal to CD. K is contained in VR. And VR closure, which is equal to, which is compact. This is the situation that you have. Okay. Now let us define or give the graph of this function. Okay. So let me draw the picture again. There is no space there properly to fit in this. So let me do this. Upon dash this, take R. This is just the scaling. This is your K. Now, or I can write this as K. And then I have CD. CD is open. So this is a some VR. Okay. And then how do you define this function? Let us draw the graph of this. So FR is then defined as 1. So FR is equal to 1 on VR. FR is equal to 1 on VR. This is the, and outside FR is equal to 0. The function is now 0 here. This is 0. So the function is 0 value here, and the function takes the value, sorry, it's not 1, takes the value R. This is 1. R is less than 1. So the function takes the value R on VR and equal to 0 in the complement of VR. Okay. What about Yes? Use the same picture. And you have, this is actually VS closure. So this is CD. So okay. Now how do you define this function? Now we define the function to be equal to 1 on this, on CD. This is 1 on CD, and S is some value less than that, and we, in the complement of this, we define the function to be equal to S. This is your GS. Okay, so these are the two functions. You have FR, this is GS. Okay, so this reference is required for later work. So that gives some feeling for what is going on. Now let me come back. Make the observation. FR is because there is some opening, it's a discontinuous function. Okay, it's a discontinuous function, but then it's a lower semi-continuous function. But GS is again a discontinuous function, but it is upper semi-continuous. These are the two crucial properties that we shall need for later work. Because this is associated with compact set, this is associated with closed set, this is associated with an open set. Okay, therefore you can easily see that these two functions have these properties. This we have explored earlier. Now define. This is the definition. Supremum over similarly, we define G as infimum over S of T. So you know that it's a bounded function. These functions are all bounded functions because you have got 1 less than or equal to f bar less than or equal to 1 G, sorry, this we do clearly. Okay. So you get two functions. Now the limit exists, and we call this the supremum, or the supremum exists. The supremum is designated by F. The supremum of GS is designated by G. Then again, once again, from something that we have already proved, that F, which is equal to supremum of Fr, each Fr is a lower semi-continuous function, is lower semi. Also, G is equal to infimum of upper semi. So we got two functions now, f and g. One is lower semi-continuous, the other one is upper semi. Okay. Therefore, what we do next? So note that f is 0 less than or equal to f less than or equal to 1, and fx equal to 1 for x belonging to 2. This is assured, and further support of f is contained in what is E1 R1 which is equal to B corresponding to 0, R1 equal to. So we have finished with that work. Right. Now what we want to prove is, so the third stage prove that what would this be? A lower semi-continuous function and an upper semi-continuous, and they are equal. So the resulting function f is then, which would imply that f is already f is equal to 1 on k, and its support is contained in what you call V naught closure. So that is done. I mean, that's the part. So that we have to prove actually. How do we prove this? Proof is not complete. This is what you want. And the first thing that you prove is that, so 3a, what we prove is this. Fr is less than Gs for every R and S being what are called rational numbers. This is what we want to work on. So we first look at the scenario R less than S. Verify in each of these cases. The case of R less than S, we have Vs closure contained in Vr. Then you have Fr R for x belonging to Vr, and this is equal to 0 otherwise. So just I am rewriting the definition. And Gs equal to 1 for x belonging to Vs closure and equal to S for x or otherwise. So what is the scenario? The scenario is this, that you have got Vs closure, this is open, this is closed. Okay. Now we have to look at all sorts of situations. One, first we take up points in Vs closure, because you know that Vs closure is contained in Vr. Okay. On Vs closure, we have R equal to Fr by definition, which is less than or equal to 1, which is equal to. So Fr is less than or equal to now on Vs closure complement, taking complement of that intersection Vr. That means this region. This is the place, and where you see that you look at the values of FR and here, and FR is equal to what? FR is equal to R, but VS is equal to, sorry, GS is equal to 1 over here and S over here. Okay. But R is less than S. Okay. Therefore, GS is equal to S is equal to S, which is greater than R, which is equal to FR, which implies FR is less than S. Okay. Now we go to the next. Well, then what is left? Then what is left is on VR complement. On the complement of VR, on VR complement, we have on VR complement, we have GS is equal to S, which is greater than 0, which is equal to F. Therefore, again FR is less than S. Hence, for R less than S, we have FR less than Now we have to look at the other scenario. This is for R less than S. Now for R equal to S. For R equal to S, you see that VS closure contained in VR. So R is equal to. So this is both VR closure and VR. Or we have VR closure, VR contained in VR. Okay. Now let us work on this. Therefore, what you have is R equal to FR on this, which is less than 1, which is equal to GS, S equal to R on R equal to S. Now you have on VR complement GS equal to S equal to R, which is greater than 0, which is equal to F1. Therefore, once again it implies FR FR is less than. So we have considered the situations R less than S, R equal to S. Now we have to consider the third scenario where R is greater than S. Now you see on this FR is less than VS. This is our claim. Suppose FR is greater than S. Then what happens? This happens only if Go to the figure and it's easy to see. R greater than S. See, we work this out. PR is contained in VS closure. Then FRX is greater than if X belongs to VR and X does not belong to. So it turns out that this is greater than Gx only if X has the property that X is in VR, but X is not in VS closure. But is that possible? It is not possible, because what happens is you have VR contained in VS closure. Okay, right? But this is what we have. R greater than S implies yes closure. VR is contained in yes closure. And therefore, you see that X belonging to VR means X is in VS closure. So, the possibility does not exist. What does this mean? Thus, what do you have? FR is this is what we okay. What is the consequence? Consequently, F is less than for every now we have to rule out the possibility that Fx can be less than Gx. Okay. Next we prove that is but how does that come? Suppose now Then we have already seen that fx is less than or equal to dx. Then for some x, fx is less than, so then there exists rationals R and S belonging to such that that means if you have two numbers which are different from 0, then in between you can interpose two rationals R and S such that R is less than. This is exactly what we are using. Now you see fx less than R implies x does not belong to VR. Look at the definition. Okay. Since G is greater than S, we have x belonging to PS closure, x belongs to S closure. But here, PS closure is contained contained in VR. This is a contract. Thus, for every x, we have that is f is equal to 0. Now just one line. F is lower semi-continuous, G is upper semi-continuous. They are equal. Therefore, F is G is upper semi-continuous. F is equal to G implies F is continuous. F is continuous. This is the. Now we also have F is identically equal to 1 on K. F is F support of S, support of F is contained in the given open set. Okay, look at the definition. Okay, therefore what do you get? Such that is contained in. So that is the thing. That completes the proof of the Urysohn's. It's very nice to see how this whole proof is built up, and that's very interesting. Thank you very much.